Hi, this is Involved Innovation YouTube channel. In this video, we will see about what is Trie data structure. Have you ever wondered what is the data structure that powers the autocomplete in the search bar? It can be Google search bar or any other search bar where you can start typing. It suggests the word which has the same prefix. This is done using the Trie data structure. Trie is a tree-based data structure. Trie data structure gets its name from the word retrieval. In Trie, we will arrange the alphabets of a word in a tree-like data structure, where each node represents the alphabet or the character in the word. So the words or string can be retrieved by traversing down the branch path of the tree. Root is the starting point of the tree. Each node represents a character. Each level represents the nth character in the word. For example, in this Trie, to check if there is a prefix IR exists, start with the root node and traverse to the level 1. Node I is present. From this node, check if any of its immediate child node has the character R. Node R is present, so the word with prefix IR is present in this Trie. If this node has any of its child as star, then that mentions this string is a word. For example, IRS is a word because S has one of its child as star, whereas INVO is not a word in this Trie because O doesn't have any immediate child node as star. Now we will see how this Trie works. We will use a hash map to store the next nodes, where the key is the character and value is the Trie node itself. And then boolean to represent the end of word. If this particular boolean is marked as false, that means this is not the end of word. If this boolean is marked as true, then it is end of word. Now we will see how to insert a word in the Trie data structure. The list of words to be entered are JavaScript, Java, C, C++, Swift, and then SQL. First we will see how to enter the word JavaScript in the Trie data structure. Enter the first character J in the root node map. This J is not already present in the root node map, so create a new entry with key as J and the new node as value. In this new node map, create an entry with A as key and new node as value. In this node map, create an entry with V as key and new map as value. In this node map, create an entry with A as key and new node as value. And then here repeat this process. We will create S as key and the new node as value, and then from there we will create C as a key and the new node as value, and then R as a key and new node as a value, I as a key and the new node as a value, and then P as a key and the new node as a value, T as a key and new node as a value. Now the string ended here. Now to mark the end of this particular word, mark the nodes is end of word boolean as true. Now we have inserted the word JavaScript in this Trie data structure. Now we will see how we can mark Java in the Trie data structure. This Java is little tricky here because already we have entered the JavaScript. This Java is already present in the JavaScript. Now we will make sure this Java is also a word. Now first enter the word J in the root node map. J is already present in the root node map, so get the node associated with J. Check whether this node map has the key A. Yes, it has. So get the map associated with this key A. Check whether this node map has the value V. Yes, it is. So get the node map associated with the key V. Check whether this node map has the key A. Yes, it has. So get the node map associated with the key A. Now we have marked is end of word boolean as false here because JavaScript doesn't end here. Now in case of Java, this string Java ended here, so we need to make sure we are marking this particular boolean as true. Now we have marked this boolean as true, so we have two different string. One is JavaScript and another one is Java. Now we will see how to enter C in the Trie data structure. Enter the first character C in the root node map. C is already not present in the root node map, so create a new entry with key as C and the new node as value. Now we have reached the end of letter. To mark the end of letter, mark this node is end of word boolean as true. Now we have successfully entered the C in the data structure. Now we have seen like A single character can be also marked as a complete word just by marking its end of word to boolean. the example C++. Enter the first character C in the root node map. C is already present. We have entered C and then we mark that as a word. So get the node associated with the character C and then check whether the node map has the key plus. No, it does not. So create a new entry with key as plus and the new node as value. In the new node map, create an entry with key as plus and the new node as value. Now the word is complete, so mark the nodes is end of word boolean as true. I will run animation to see how we can enter the Swift and then SQL in this Trie Data structure. Now we have seen how to enter a word in a Trie Data structure. The time complexity of entering a word in the trie is order of n, where n is the length of the string. For example, if you are entering the word JavaScript into this trie, that means the JavaScript has 10 characters. The time complexity is order of 10. So to enter a word, the time complexity is order of n. If you want to enter k words into a Trie Data structure, then the time complexity is k into n, where k is the number of words, then n is the average length of this k strings. The space complexity can be approximated by k star n, where k is the number of words and n is the average length of this k strings. So now we will see how to search for the words in the Trie Data structure. We can do two kinds of search in the Trie Data structure. One is prefix based search or the whole word search. In the prefix based search, that is the one which we will be using in autocomplete. For example, if I am searching something like IN, Google search engine or some other search engine will give us the top n number of words which has the same prefix. This is done using this prefix based search. The prefix based search checks whether the word with the given prefix is present in the Trie Data structure or not. First we will start with Java. First start with the root node. Check if the character J is present in the root node. Here J is present. So get the node associated with the J. Check whether A is present in this node map. Yes, A is present in the node map. Get the node associated with the key A in this node. Check whether V is present in the node map. Yes, V is present. And get the node associated with the V in this node. Check whether the A is present in this node map. Yes, A is present in the node map. Thus by we can able to see the prefix Java is present in the Trie Data structure. We will check whether SQ prefix is present in this Trie Data structure or not. First start with the root node. Check if the character S is present in the root node. Yes, here S is present. So get the associated node for the key S. Check whether the Q is present in this node map. Yes, Q is present in the node map. So the prefix SQ is present in the Trie Data structure. Now we will try to search a prefix which is not exist in this Trie Data structure. For that I will use go. Check if the character G is present in the root node. Here the G is not present, so return this prefix is not present in the Trie Data structure. You have a number of words in this Trie Data structure and none of the word has the prefix go. And we will also see like a bigger word whether a scalar is present as a prefix in the Trie Data structure. First start with the root node. Check if the character S is present in the root node. Here S is present. So get the node associated with the key S. Check whether C is present in the node map. Here the C is not present in the node map. So here we no need to search the remaining character, and then the prefix scalar is not present in the Trie Data structure. The time complexity of prefix based search in the trie is order of n, where n is the length of the prefix. Now we will check whether the complete word is present in the Trie Data structure or not. This is little different than the prefix based search. Value is present in the tree. In addition to that, we also need to check whether that is a complete word or not. Now we will check if the words Java, C, C++, and SQ, C# present in the Trie Data structure or not. First we will check whether the Java is present in the Trie Data structure. First start with the root node. Check if the character J is present in the root node. Here J is present, so the node associated with the key J. Check whether A is present in the node map. Yes, A is present in the node map. Get the node associated with the key A in this node. Check whether V is present in the node map. Yes, V is present in the node map. Get the node associated with the V in this node. Check whether A is present in the node map. Yes, A is present, and they get the associated node map. Now we need to check whether the is end of word boolean is true here or not. Here the is end of word boolean is true, so the word Java is present in this trie data structure. Now we will check a very simple example which we have already entered, the C. Start with the root node and check if the character C is present in the root node. Here C is present, so get the node associated with the C. Now check whether the is end of boolean is true in this node. The word C is present in the trie data structure. Now we'll run an animation to check if C++ is present. And C++ is present here. We can able to see the is end of word boolean is true when we have completely traversed the C++. Now we'll see whether the SQ is present. Check whether the character S is present in the root node. Here S is present, so get the node associated with the key S. Check whether Q is present in this node map. Yes, Q is present in the node map. Now get the node associated with the Q in this node. Now check whether is end of word boolean is true here. Here the is end of word boolean is not true, so we will mark this SQ as a word does not exist in this trie data structure. We will also try C#. The hash is not present, so this word is not present in the trie data structure. The time complexity of searching a word in the trie data structure is order of n, where n is the length of the word. And we will also see how the deletion operation happens in the trie data structure. We will delete Java, C, SQL and then C++. First start with the root node. Check if the character J is present in the root node. Here J is present, so get the node associated with the key J. Check whether A is present in this node map. Yes, A is present. And traverse till we have reached Java and get the node associated with the key A in this node. Here this end of word boolean is true. Now to delete this word, we need to make sure we are marking this true to false. So if you are marking this true to false, that means this Java word is no longer present in this trie data structure. By this way, you can delete Java in this trie data structure. We will also try another example, deleting C. So first start with the root node C, get the node map associated with the C. So check whether this node has is end of word boolean is set to true. Here it is set to true. Now change this to false. Now we have removed the C from this trie data structure. Now we will see how to delete SQL. To delete SQL, start with the root node. Check whether the key S is present in the root node. Yes, key is present. Traverse to the node referenced by S. Here check whether we can able to find Q. Yes, we can able to see Q here. And then traverse to the node referenced by Q. And here we can able to find L. And then traverse to the last node. Here we can able to see this node doesn't have any keys and this node only has true. So in this case, we no need to mark this, but we need to delete this completely. So here in this case, to delete key Q, we have C++. So for C++, we will start with the root node C. We will get the node associated with the key C. Here check whether we have plus. We have plus. Get the node associated with the plus. And check whether we have plus here. Get the node associated with the plus. And here this node is also completely empty. We don't have any keys. You can delete this empty node and then you can delete the plus node and then you can delete the plus. The time complexity of deleting a word from a trie data structure is order of n, where n is the length of the string. So now we will see this with the coding example. For this I am using Java, but this pseudocode can be applied to anything. First, if your trie only accommodates alphabets, then you can give it as an array where you can initialize it with 26. But in this case, the key is a character and then the value is another trie node. So the trie node holds the map and then boolean. So the boolean is end of word. Also has a constructor for this trie. The constructor holds the root node. So the root node is the starting point. We need to always make this reference explicit so that we will always start from the root node. We will have these methods insert search starts with and then delete. Now we will see insert. First we will get the root node, traverse the word length. If the character is already present in the map, then just get the associated trie node. If not, create a new trie node and associate it to that character. Once you have traversed this complete word, make sure you are marking this end of word is true so that you are marking this word is present in the trie. To search, start with the root node and then traverse through the word and here start from the root node, check if the node contains the key. If the node contains the key, then get the node reference and then search the next character is present, the new node map, and do this for the length of the string. If any one of the character is not present, then return false. That means this one is not present. Once you have reached the last, if the is word end is false, that means this is just a prefix, this value is not present, so return is word end. Next we will do the starts with. The starts with is similar to the word search, but here in this case, instead of checking the node is word end, if you are traversing and if you can able to find all the characters from root node to the nth node, then we can able to return true. If not, we can return false. So for delete, first we will check if the node word is null or word length is 0, then we are returning it. Start with the root node. Here I will create two different placeholders, one to hold the node to remove the key, another one is the character to remove. We will start with the 0th index. We will get the map associated to the node. So here we are getting the node associated with the element, and then we are checking if the node is null. If the node is null, that means this value is not even present in the trie, so we can return it here. So here we are checking two different things. This is very crucial. We are checking if the node has more than one key, or if the node is word end is true, then we are capturing this node and we are registering this in node to remove key, and then we are registering that particular element in key to remove. For the next iteration, we will reference the temp node to the node, and then we will continue this iteration. Once this iteration completes, if the node dot is word and is false, that means here this word is not even present in the trie, so we will return that. If the last node has empty hash map, then we can delete this character from the node to remove key. Now we will see why we are doing this logic. We will see this with SQL. Here SQL we have S is the first starting node, and here traversing to the next node referenced by S, and then here we have Q. Here this particular node has a map which has two keys, so this we are registering, and we are registering Q here. And then we are going to the next iteration. Here we don't have multiple keys, so we are not registering this. The is word end is also not true, so we are not registering this. The node references this last node which doesn't have any key. If this node is empty, then deleting the key from the node to remove. So here the node to remove is this one which has W and Q, and here in this case we are deleting the Q. If you are deleting the Q, we are deleting this off completely. We are not deleting this complete node because W we need, and that is needed for Swift. And we will see this with another example. Here in this case we have C++. If you see in C++ case, we have C, and the next node which is referenced by C has only one key, but here we have marked this node as true because C is a valid word in this trie. So we are registering plus as the character, and we are registering this node, and we are going back to the next node, and here we are not registering this node because this has only one element and the is word and is false here, and we are going back to the last node. Here we don't have any key, so if we don't have any key, we have already registered this node, and then we have already registered the character plus. We are deleting the plus and associated nodes from this particular node, so that leaves us with C. We will see this with small test cases which I have written. Here I have written a JUnit test to test the scenarios. I also written a draw tree method which draws out the elements in this trie. So here I am entering JavaScript, C++, C, Java, Swift and SQL in this trie. Here this is not case sensitive because here in the trie I am marking everything to uppercase, deleting the C here. So if I execute this particular delete C, before deletion, and the node referenced by the C has the value set to true. So is word end is set to true here, and then we also have C++, and then this is ends to true. So after deletion, the node referenced by the value C is marked now false because we have deleted C. Here I am deleting out the JavaScript. Run this delete JavaScript, You can able to see this JavaScript has all the nodes JAVA, and here the A referenced node is end of word marked to true because this Java is also a valid word which we have entered. And here after JavaScript we can able to see that node doesn't have any key associated with it, but it is marked as true, so that means this is a valid word entered in the try. So now after this deletion you can able to see only JAVA, and we can't really see anything after A. That means we have removed SCRAPT completely from our try. So we can also see this example with SQL. Now if I run this, here we can able to see before deletion we have SQL, and here we have Swift also as part of this S node. After deletion we don't really see any SQL here. This S node only has a node which has only one key now. It doesn't have two keys. In previous case you can able to clearly see we had like two keys, one is Q and another one is W, but after deletion we can able to see only W. Thanks for watching this video. I believe this is clear, and if you have any questions, post it in the comments. If you feel this video is helpful, share it with your friends. Subscribe to the channel for more technical videos. Thanks for watching.